Buenos días, estamos listos para comenzar. Pues bienvenidos a todos de nuevo a este seminario del Departamento de Oceanografía Física. Me da muchísimo gusto verlos acá. Y el día de hoy también tenemos otro invitado de los especiales que hemos tenido en toda esta serie. Entonces les agradecemos mucho que estén por acá, también a los que están conectados en YouTube, en Facebook y aquí en el Zoom institucional. Miren, el día de hoy vamos a tener un seminario bilingüe. Tenemos aquí uno de nuestros, pues nuestro ponente de hoy habla muy buen español, pero va a dar su charla en inglés para evitar hacer brincos de tecnicismos. Pero bueno, al final pueden hacer sus preguntas en español, en inglés, en portugués si se animan. Tomás, aquí tenemos, sí, luego platicas un ratito con Miguel, que es portugués, aquí investigador nuestro. Bueno, pues Tomás es brasileño, está ahora aquí de visita, pues estuvo aquí un par de días y bueno, tiene temas bastante interesantes, ¿no? Es bastante joven, pero ha trabajado en muchos temas y bueno, un montón de habilidades técnicas. Para que al final también se queden al queso pan y vino, a platicar un poquito con él. So we're going to switch to English now, and so I'm going to read your CV, Tomás. He is an assistant research scientist in the Department of Atmospheric and Oceanic Science at the University of Maryland, where he works in Jacob's Wenegrad's group. And he's also a computational research scientist at atdepth MRB. He earned his PhD in atmospheric and oceanic sciences from UCLA in 2020, where he was awarded the Jacob Yernes Memorial Award and the Richard Turco Exceptional Research Award after completing earlier degree in environmental engineering at the Federal University of Paraná in Brazil. Prior to his current appointments, he was a postdoctoral associate at University of Maryland for 5 years. His research centers on small and submesoscale turbulence in the ocean, which he investigates primarily through turbulence-resolving large-eddy simulations. His work spans a range of processes, including surface boundary layer turbulence, Langmuir circulations, submesoscale instabilities, and flow topography interactions, with a common thread of using high-resolution simulations to prove how small-scale dynamics shape larger-scale energetics, mixing, and material transport. He is also an active contributor to open-source scientific software, notably the Oceanigans Julia package and Oceanostics, and a proponent of open, easy-to-reproduce computational science. Así que, pues, bienvenido, Tomás, y adelante.
Hola, ¿me escuchan bien así?
Sí. Está abierto se escucha muy bien. Si no, me avisan y yo te digo.
Bueno, entonces voy a presentar en inglés nomás porque en español me tarda un poco para encontrar los términos técnicos y quiero estar aquí en buen tiempo, ¿no? So I'm going to switch to English. But if you have any questions and you want to ask in Spanish, ask away. It's fine. I'll try to answer my best in Spanish. And please feel free to interrupt me if that's okay. If you don't understand anything or just like with general questions about the science. Right? All good? So thank you so much for being here first, and thanks for the invitation. It's been a pleasure to be here. And we're going to talk today about some research that I've been doing that looks into flow topography interaction, so flow in the bottom of the ocean. And this is kind of the roadmap that we're going to go through. So first, I'm going to go over a brief introduction about like why I'm looking into this, why this matters, right? And then just how I'm going to look at them, because I think here in these groups, like in this department, most of you I think use large scale. You look at large-scale phenomena, and I'm looking at things at large scale sometimes, but with a small-scale bias. So I might be using some techniques, numerical and otherwise, that maybe you're not familiar with. So I wanted to spend a little bit of time to make that a little clearer to you. And then part 1 and part 2 were really like two separate papers that I published recently that I think are nice to talk about. And then we're going to conclude with some synthesis, right? So first of all, why am I looking at this, right? Why does this matter? I believe most of you are probably familiar with Walter Munk, right? And like a few decades ago, he was looking at the ocean circulation and calculated a given amount of mixing that the ocean should have in general to support the global circulation that we were observing, right? Things need to be in balance, but he wasn't finding a mixing, and eventually he published another paper about it, which is this paper that I'm citing here, which was, I think, it was in 1998, where he revisited his prior assertions. I was like, okay, so maybe we're not finding the mixing that we should be finding, so maybe instead of mixing uniformly, the ocean is full of specific spots with a very high mixing, and otherwise it doesn't mix much, right? So he posited the now famous question, which I include in all my talks because it's almost mandatory, because it's a famous question, like, are seamounts the steering rods of the ocean? And by steering, I think he actually meant like mixing, right? Because mixing is reversible, steering is reversible. So I think that are seamounts the mixing rods of the ocean? And so that's what he posited, but at the time he didn't have a ton of tools to pursue that question. But over time, we've begun to research that question, and it turns out that we think the answer is yes, actually. I mean, not just seamounts are a small part of it, but I think like bathymetry, rough bathymetry or bathymetric features are steering rods of the ocean, right? So some of the evidence here is some recent evidence. If you look at Mashayek and others papers from 2024 at PNAS, they found that mixing due to seamounts, bathymetric mixing due to seamounts, are actually very important in the total mixing that happens in the ocean. And actually, if you look at the Pacific, they're leading order. So here are all the seamounts that they considered. And here in orange, you can see the mixing associated with these seamounts specifically. And I will mention that the seamounts that they looked at are only a subset of the seamounts that we have cataloged. So there are way more seamounts here in this data set that I plotted, which itself is a subset of all the seamounts that exist. And seamounts are a subset of the features of the ocean that mix. So, really, I think we should expect a lot of mixing from features in the bottom of the ocean in general. Another paper is the one by Jonathan Gula in, I think, 2016. Yeah, 2016. And they looked at one specific interaction in the Bahamas, and where they can extrapolate from that, and they found that the topography dissipates about 0.1 terawatts. And just for a point of comparison, the wind is thought to inject 0.8 terawatts into the ocean, so an eighth of the injection just by the wind. So there's reason to believe that this is actually an underestimation on the part of Jonathan Gula. I'm going to make that case a little bit later. But even here, even if it's a proper estimate here, it's significant, right? It's not leading order, but it is significant, right? So that was the paper by Jonathan Gula. And there's been a lot of recently. There's been this uptick in interest in this sort of question, and I'm not going to go over all the findings here because really they're too much to go over in just like a brief introduction. But I will say that the literature is revealing like very complex dynamics and energetics that come from these interactions, because you can change the stratification, you can change rotation, you can change the geometry, you can change the tides, you can change a lot of things. And the dynamics and energetics, they respond in ways that aren't always obvious. There's always some complexity there. Right, so I'm citing here 5 papers that looked into that question recently. And all these papers, by the way, they used Reynolds average, Navier-Stokes in one way or another. So, regional models, ROMS, Krakow, MIT GCM. There's actually very few papers that resolve the turbulence. So I'm citing here 4 papers, and they're all from one group, from Sutanu Sarkar's group at UCSD, San Diego. And I think, so here's where I come, right? Resolving turbulence is important, I think, because if the question is about mixing, like mixing and dissipation is necessarily performed at the end of the day by small structures, right? By the small scales, close to the Kolmogorov scale. And the Rand's closures like K epsilon, like KPP, or whatever you prefer to use, they're always going to parameterize important processes there, because if you can't resolve them, you have to parameterize them. And no matter how good a parameterization is, it's never going to be perfect, and it's always going to make some assumptions that are going to be flawed at some points, right? And in particular, one thing that they haven't resolved is submesoscale instabilities, which generate a very different kind of turbulence. So there's probably work on that. That turbulence that you generate from, for example, this pure surface forcing is very different from the turbulence that you generate from surface forcing plus submesoscale, right? It mixes different. It dissipates things different. So there has been a gap in the previous body of work looking at this type of interactions, right? So yeah, so this is the point. So these instabilities are not resolved. So in these papers in particular, they talk about submesoscale instabilities in the sense that they see the conditions, they generate the conditions that are supposed to generate those instabilities. And here I'm talking about centrifugal instabilities. I'm not going to talk too much in detail about that because that's a whole other talk. So you see conditions that would generate symmetric instabilities or centrifugal instabilities, but you can't resolve those instabilities. So definitely like an important step, but I don't necessarily trust the mixing and dissipation that these models generate, because they're parameterizing a lot of the important dynamics. And so the idea here is to resolve bottom turbulence and to resolve the conditions that lead to bottom turbulence. And that that specifically includes submesoscale instabilities, like symmetric instabilities. The problem is that the traditional methods we have to investigate these questions or these instabilities, they don't really resolve submesoscales, right? Or they resolve submesoscales, but don't resolve the turbulence that comes from submesoscales. So for example, if you look at traditional ship-based measurements, you can measure microstructures and you can get the smaller scales really well, but it's kind of, submesoscales are kind of an awkward scale for ship measurements to measure. You can definitely do some specific techniques, but it's not optimal. If you go to remote sensing, that's larger scales, and you have SWOT, which is putting a little bit of the smaller scale range in there. In regional models, you can resolve the submesoscales, but you don't resolve the turbulence that comes from submesoscales, right? And that's where large-eddy simulations come from, which is my tool of choice. I'm going to talk a little bit more about that. But basically lies kind of in this middle. And up until maybe like a decade ago or a few years ago, we didn't have the computational resources to investigate submesoscales with that, because it was the largest domains you could represent was something like 2 kilometers in horizontal domain, 2 square kilometers, right? 2 by 2 kilometers. But now we actually are able to resolve bigger and bigger domains, so we're getting the submesoscale right, which is great. So I'm going to talk a little bit about large-eddy simulations. I don't know if is anybody super familiar with large-eddy, or is anybody better not familiar at all with large-eddy simulations? Okay. So I'm not going to go into super detail because again, that's a whole other talk. But the gist about large-eddy simulations is that you're going to resolve the forward cascade down to when the eddies become isotropic. And then you start to parameterize them. But the difference between a parameterization from large-eddy simulations and a parameterization that you get from Reynolds average Navier-Stokes is that when the eddies are isotropic, the behavior is somewhat universal. Right? You can apply Kolmogorovian theories to it, if you have heard of that. And no matter if you reach isotropy through this force or that force or in that condition, supposedly isotropic eddies, they kind of behave similarly. So the closures for large-eddy simulation are very faithful. And that is important for me, for this research, because then you can trust the energy cascade and you can trust a little more. Obviously, it's not perfect, but you can trust a little more the dissipation and the mixing that comes as a result of these smaller isotropic eddies. Does that make sense? Oh, good? Okay. And so that allows me to investigate some mesoscale instabilities and the boundary layer turbulence and all the small scale turbulence that comes from that in a way that's way more trustworthy than Croco or ROMs or using k-epsilon, that kind of stuff, right? And most flow topography studies before that, they don't do that. So that's the gap that we're trying to fill here. And so this is an example of one simulation that has just a barotropic flow going past the headland. And that's the first paper that I'm going to talk about, actually. And all those simulations that you see here, I'm using Oceanic, which some of you were in the tutorial yesterday. That's basically the tool that I've been using for a few years. And yeah, I basically in these simulations, that's all you're going to see is whatever Oceanic is doing. The caveat here is that I want to talk about is that we have to assume dynamic similarity if you want to do something that's really big. And the assumption is, if the geometry is the same, if you're getting, for example, a seamount or a headland or whatever that's tons of kilometers wide, if it's a high enough Reynolds number, and if the non-dimensional numbers that are relevant for the dynamics are the same, which in this case are these non-dimensional numbers here, that we're going to talk about in a second, you can shrink down or scale up that simulation, and it's going to behave basically the same, right? Maybe you have to put a coefficient in front of some results to scale up or down, depending on the size, but dynamically, they're going to behave the same. So that's a caveat here. That's something I'm assuming. But in general, that's a pretty good assumption. It's been shown to work very well, right? So it's kind of a standard approach in large-eddy simulation, right? And in this case, in the simulation that we're going to present, there are three important independent non-dimensional parameters. One is the Resumen number of the bathymetry, which is defined here like you would define you would expect. So velocity, size of the bathymetry, and rotation. Fruit number for the bathymetry, which again, velocity of the flow, the height of the bathymetry. So this is people call it sometimes vertical fruit number, and the Brunt-Weisshaller frequency, so the stratification frequency, and the slope, which basically is the geometry of the obstacle, right? A very steep seamount is different from a very shallow or a very flat seamount. That's pretty much it. And if you get this three-dimensional parameter space, you can also define that's what I'm calling here a slope Berger number, which is the Rossby over fruit. But this, so you can see that this isn't an independent parameter; it just comes from these parameters that are already there. And this is going to be a very important parameter in these simulations because you're going to see that this organizes a lot of things. Let's check the time so I don't go over time. And if you forget a little, so this is two of these parameters, so the Rossby and the fruit number, we actually have some data on where the seamounts that exist that we have cataloged fall into the parameter space, so we can cater the simulations pretty accurately to a representative part of this parameter space, right? So you can see this is a joint probability distribution of these parameter spaces based on the seamounts that we know. So I'm going to run something that kind of covers this big spot here because that's where we have the seamounts that we know. Okay, so that's all for the intro plus methods. So first I'm going to talk about how turbulence organizes these things, organize dynamics in these weeks. And here I'm going to focus on headlands just because it was an easier first step. So all the simulations have this sort of geometry. It's kind of a headland, like an intrusion into the flow. And flow is going to be coming in through the right, doing whatever it needs to do, whatever it's going to do when it interacts with the headland, and then it's going to come out the other side, and I'm going to measure things in the meantime, right? So basically I ran, so this is the parameter space. So the blob that you saw before is around here. So I'm running 16 simulations, so each in a different part of parameter space because I want to cover the parameter space as well as I can. And I think this was the first large-eddy simulation to resolve the full forward cascading these configurations, actually. And I'm doing this in an anticyclonic way because wakes, since it's just one-sided, you have to pick which side. I'm gonna show a little bit of some results in the cyclonic wake, but I'm gonna focus on anticyclonic wake because those are dynamically more interesting. And each of these simulations is a little bit different from the other. But what happens when you explore these simulations is that you actually have 4 major regimes that you can identify here. So if you have, if you're here in the bottom right, you have this simulation here, or this simulations that look like this simulation here, where the flow is kind of following the terrain. Right? It's not super interesting, but the flow is following the terrain. If you go to the opposite end, here in the upper left, you have simulations like this, where there's a wake, an eddy in the wake that's attached to the tip of the headland. And here you have lots of, I'm going to talk a little later about that, but you have symmetric instabilities because you have very negative potential vorticity coming out of it. If you go to the bottom left here, you have something a little bit different, where you generate eddies, but those eddies detach, right? And they go and have a life of their own later. And you can see that the potential vorticity here, which by the way is what I'm showing in the colors, potential vorticity, is almost zero at the time that it detaches, because some symmetric instabilities killed here the negative vorticity, if you know what that means. And if you go to the upper right, which is high Rossby, high fruit number, then you get to a regime that's very similar to just three-dimensional turbulence. Like if you were running this in a lab without rotation, right? It's like a big bathtub, pretty much, right? So very small eddies straight away. So we have, so I'm going to go over some of the major results here, but I'm not going to spend too long on that because otherwise I'm not going to be able to finish the talk. But you have evidence here of centrifugal instabilities, which again is something that has been posited by earlier simulations, earlier studies, but it didn't resolve it. So there was always the question, like, is it really are they really gonna emerge? Are they not gonna emerge? But apparently they do happen. So what you're seeing here is your tail potential vorticity, and then you're seeing 6 different vertical cross sections down, progressively more downstream from the headland, right? So it starts here, then comes here, etc. And you can see that. I mean, I'm not gonna. I'm trying not to go into too much detail because otherwise I have to explain a bunch of stuff. But when you look at the wake here that's being detached, so this blue stripe here, meaning that the band of negative potential vorticity, that is exactly where you would expect centrifugal instabilities. And you do have lots of little overturning movements, which are a sign of centrifugal instabilities. Not only that, but you can see that the potential vorticity is getting more and more towards zero as you go downstream, which is again exactly what centrifugal instability would do if it happened there, right? So this is a very strong sign of potential of centrifugal instabilities. And in fact, if you run the same simulation, but for a cyclonic wake, so here I'm just flipping Coriolis, you have a very different evolution, meaning that you don't have actually centrifugal instabilities, you have very, very few instabilities. So the wake actually retains its form throughout, and you can see that even after the eddy detaches, the wake has the positive PV sign, right? It doesn't go to zero because there's no instabilities there to make the PV go to zero. Hopefully that wasn't too confusing. I'm kind of trying to give you like a big results, but without getting into the nitty gritty, otherwise we won't have time. So just like flipping back and forth, the wake here is being destroyed by these instabilities. You can see that there's a lot of small scale movements, but here it retains its shape, right? So this is just comparing them. You can see something's going on there, and it's centrifugal instabilities. Now remember the slope Berger number. As you go to higher and higher slope Berger numbers, there's also an organization of the flow where you start to see these bands of these different bands that are decoupled vertically from each other. So you have very high shear, bands of very high shear. And this is a simulation that has the highest slope Berger number in the top left. And you can see that it has those bands very, very well defined, right? And as you go to the bottom right, which is very low slope Berger number, they start to disappear, right? So that's one organization that, again, had been posited from previous studies, but they hadn't been resolved yet. So it's nice to see that they actually happened. So this was predicted by some papers before. Sorry. And if you go, let's talk a little bit more about dissipation now, dissipation mixing. Again, slope Berger number, it organizes the results from mixing and dissipation really well. So what you're seeing here is dissipation at the top, mixing at the bottom, and you're seeing the X average, the mixing and dissipation. So basically, dissipation and mixing as a function of downstream distance from the headland, right? And the slope Berger number is colored here from blue to red. And as you get to red, or as you get to like higher slope Berger numbers, you can see that the peak of dissipation happens more and more downstream. Not only that, but dissipation starts to get higher and higher, right? So you have little dissipation, but very close to the headland for low slope Berger number. Then it starts to do this, and this as you keep increasing the slope Berger number. Same thing for mixing. I mean, if you squint, these pictures, like the upper and lower panel, they're pretty much the same, right? They're very similar to each other. And so there's this organization. And actually, if you collapse these curves and take an average of these curves, meaning you have an average of the dissipation and mixing throughout the whole simulation, you actually get this graph, which to me is pretty remarkable because they interact, they fall almost perfectly on a straight line for the headlands, right? So each color here is a different regime, right? I'm separating here in three colors, three regimes, but really like it's four. I'm just simplifying it here a little bit, trying to make the Brazil flag, I guess. And you can see that it falls very close to like a one-to-one line with slope Berger number. So if you double the slope Berger number, you can expect to double the dissipation, and you can expect to double the mixing also. The mixing, maybe the R square is not that nice as the dissipation, but it's also very close to one. And reminder here that also buoyancy mixing, in the end, it ends up translating into deep water upwelling, right? So this can have pretty important implications for the global circulation, because it's still an open question about how the upwelling happens on a large scale for the global ocean circulation, and this probably is one of the pieces that we need to take into consideration. So this is pretty remarkable, and I just want to put this there and remind you that this is how all these simulations look like. They look very different from one another. You have this huge range of dynamical regimes, but if you calculate the slope Berger number, put it all averages in a line, they organize in a line, which I think is pretty remarkable. I don't know why that happens still. If you read the paper, I have a hypothesis there which has to do with the drag, because the drag is very close to linear too, up to a certain point. But then if you ask me, why is the drag linear? Who knows? So, if one of you guys has a hypothesis that you want to share with me, please let me know. And I'm going to go over the next few slides just pretty fast, just some results here and there. The diffusivity also organizes pretty well, but in a way that is different from the diffusivity organization from previous papers. But previous papers didn't resolve the turbulence, so it seems to be a result that indicates that turbulence really is important when you're trying to use eddy diffusivities to model these things. Cyclonic headlands, they also organize it really well, but it doesn't seem to be a one-to-one line. The slope seems to be a little shallower, right? It seems to be a square root type law. So the anticyclonic results here in blue is cyclonic in red, and that's for both dissipation and mixing. So still an organization, just a different slope. And if you compare my results with results from previous papers, and here I'm using Jonathan Gula's results for the Bahamas as an example, you can see that the dynamics are pretty similar, but the dissipation in our simulations ends up being much higher, even after you scale it up and take the different scales into consideration. So, which is to say, like, to repeat what I said in the beginning, there's some reason to believe that the dissipation that Jonathan Gula and Ali Mashayek and their respective groups have measured is actually like an under prediction, right? Okay, so let's see the time, 12. Okay, so now I'm going to talk about the second paper, which just got published, I think last month or something, which is how much does this small stuff matter, right? So in the headland paper, I was looking more into the dynamics, and we also looked at the dissipation and everything, but headlands are a very small part of the topography that we have in the ocean, right? Basically, it just happens on the coast. We have way more seamounts. Seamounts are spread out throughout the whole seafloor. So these have a better chance to actually be impactful in the global ocean and global budget. So we're going to look at that and try to get some quantification out of that. And I'm using a similar strategy as the headland paper, meaning I have this seamount here, and there's flow coming in, barotropic flow on one side, interacts, that's what everyone wants to do, comes out the other side. One difference is that if you look at the seamount, it is rough. So there's some roughness to the seamount. And that's one thing I'm going to focus on here. So a mini introduction to this paper is that previous investigations, both with Reynolds average Navier-Stokes equations or large-eddy simulations, you always tend to use smooth seamounts, myself included, in the headland paper, because it makes things much simpler, right? But the ocean is not smooth, right? And that includes some realistic simulations, because if you're using sigma coordinate models and you don't smooth your bathymetry to make the slope a little bit flatter, to eliminate the high points of slope, you can have errors in the pressure solver. So generally, when you're using those sigma coordinates, there's the smoothing of the bathymetry. So even realistic bathymetries are often smooth, artificially so. And there's some atmosphere work that suggests that roughness is important. So this is a seminal paper by Chor in 2002. Well, I shouldn't say it's seminal because it was a review from a couple of papers of his that were pretty seminal. But it shows, I think this is at the Alps. Yeah, the Alps. But one of them is the actual Alps, and the other is like a idealized representation of the Alps. And you can see that the potential vorticity here, the signature changes a lot downstream from the mountains that you're simulating. And in particular, you have these bands here, negative and positive potential vorticity, which again have dynamical and energetic implications, because potential vorticity is dependent on if it's positive or negative. You can be unstable to symmetric or centrifugal instabilities or not, which has implications downstream. And actually, a year later, he actually analyzed some data of the mesoscale alpine program, some measured data in situ, and you see these bands of negative and positive PV. So corroborates that a little bit. There are some other papers around that. All that to say that there's reason to believe that the small scale is important, the roughness is important. So let's study that a little bit. Let's look at some rough topography. Let's start out by covering the parameter space of seamounts that I was talking about earlier, with two different kinds, running simulations, right? Two different kinds of seamount for each point of parameter space. One is the original bathymetry, and this is the Balanus seamount in the New England seamount chains, right? This is actual data that they have there, and I picked that one because it's very well studied. We have a lot of data, it's pretty good over there. And then I'm going to smooth it, a version that's me smoothing it in a way that a simulation usually would. Like if you run ROMs with sigma coordinates, you would smooth it kind of like that. I'm overdoing it here a little bit, maybe for dramatic effect. But I wanted to make it look like a Gaussian, right? With the approximate shape, and that's what I got. So the mass is somewhat conserved, and the maximum height is somewhat conserved, and importantly, the slope is somewhat conserved. So the geometry is about the same. And remember, for the headland, we ran, and we got this linear slope here for this. So this is dissipation as a function of slope Berger number, right? We got this result. The colors here are a little bit different because I'm actually separating four regimes here, but it's the same data as you were seeing before. I just color the different because I couldn't find the other figure. If you run the seamounts with and without roughness, you actually get two different results, which is interesting. So if you run, so the blue one is the smooth seamount. And you see that you have also pretty good agreement with a one-to-one line. Maybe not as good as on the left, one could argue, but pretty good agreement. And the blue dashed line is a one-to-one line with slope Berger number, right? If, however, you include roughness, you get a pretty good, a somewhat good, also one-to-one line for high slope Berger number. But as you get to like these middle slope Berger number, like one here, for example, you actually get a behavior where the dissipation stays the same, approximately, right? So you have these two different organizations. Okay, that's pretty interesting. That's for dissipation, right? What happens for mixing? Mixing is similar. So the case for mixing is maybe a little bit weaker, right? For the one-to-one line, but you also have something that looks a lot like one-to-one line for headlands, and then for the seamounts, it's a bit of a it looks the same here if you look at the blue and the red ones, but for example, the difference between these 2 points is about 3 times, because you can see that this is a log scale, and these are many scales of the log scale, right? And also there's a question here that I'm gonna not talk about, but it's kind of up in the air if this for seamounts is a 1-to-1 or 1 to like square of slope Berger number. But what is clear is that as you go to lower slope Berger numbers, the rough seamounts dissipate more. They dissipate about an order of magnitude more. Well, for dissipation, right? It's an order of magnitude more than for this, rough versus smooth. For mixing, is about 3 times more, which not as much as an order of magnitude, but still pretty relevant difference. So okay, you have the difference, but are slope Berger numbers seamount important, right? Maybe, because maybe not. But they actually are pretty important because coincidentally, this regime, so the regime for slope Berger number in seamounts, coincides with the Southern Ocean, which is exactly where the ACC is. It's Antarctic Circumpolar Currents, right? So this is a plot. This is from Ali Mashayek's paper, and the color here is slope Berger number, actually Berger number, which is in the way he defined like the square of my slope Berger number, but never mind that for now. The point is that the places where we have slow Berger number and the low slope Berger number is in the south. And if you integrate our dissipation, you can see that actually the total dissipation depends on the slope Berger number here, or because it's a linear scale with slope Berger number that we have just found out. I'm going to put rho over fruit number here, which is the slope Berger number. It depends on the width of the seamount squared. Right, so obviously bigger seamounts are going to dissipate more just because they're bigger, right? So they have bigger area. But importantly, it's the cube of the velocity also that goes into the scaling law. And ACC is a place where the velocities are very fast. So here is the slope Berger number plot on the left for each seamount, and on the right is for the same data set, a velocity of the plot of the velocity around the seamount. So you have extremely high velocities here in the ACC, exactly where roughness matters a lot, right? In the regime that matters a lot. That's pretty much a coincidence as far as I can tell. So I'm gonna explore that a little bit in a second, but before, let's look a little bit of the dynamics. So the large scale dynamics don't really change much, only the small scale. So if you look at it, so this is from another paper, and if you look at this solution, this is the Z average vorticity divided by Coriolis, right? My simulations on the right, they don't change. They're about the same. They have like this little band here. And from rough to smooth, they look about the same, except that the rough has more small scale stuff going on, has more turbulence. So that seems to be pretty straightforward. And that also matches the analytical solution that you would expect from quasi-geostrophy, just again, with turbulence on top of it, which it's nice that fits the prediction, but it does change, like I said, the turbulent dynamics. You have way more turbulence, and then you have those PV banners that I was talking about that you see in the atmosphere. You see that also in my simulations, right? Because with rough topography, the flow separates in some of the mini peaks, and that generates negative and positive return potential vorticity. And the anticyclonic side is more turbulent, which again is expected because of centrifugal instability. So far, so good. But more turbulence, more dissipation, and that's where things become different because then the energetics change, right? The colors on the left are the rough seamount, and the colors on the right are the smooth seamounts. And it might not look here because I'm using a log scale, but on the left, we have about an order of magnitude more dissipation than on the right, and like about 3 times more mixing than on the right, which matches the lines that I was showing you before, the data points that I was showing you before. And both those things closely track, obviously, where the turbulence is. So, so that's the easy part. One interesting thing is that for whatever reason that I have not been able to figure out, the mixing happens, and to some extent, the dissipation happens more up in the water column if you have rough seamounts, right? Then if you have smooth, so rough on the left, you can see that the footprint of the mixing is kind of like mid-depth of the seamount. But if you make a smooth seamount, the flow kind of follows the seamount, and the dissipation and mixing happen very close to the bottom. I haven't been able to figure out what that is. Somebody has ideas, I'm all ears, so please let me know. Okay, so those are the results in bulk. I guess the question is, how smooth is too smooth? So if you're going to parameterize these things, what's the resolution that you need to have? Like, how much of this roughness do you need to have so that you have a reasonable result? So for that, I'm going to focus on one part of the parameter space, which is a representative seamount on the Southern Ocean, right? So a small slope Bergen number seamount. I'm going to progressively smooth it in different. I'm going to progressively smooth it and run different simulations, right, for each level of smoothness until we reach the level that we had before. And this is kind of what we have. So let me go slow here. First, the points and the crosses are pretty much the same, except that I'm like rotating the seamount just to make sure that what I'm seeing is not like a function of, precise orientation of the seamount, right? Because it could have been it. I could have just gotten really lucky or unlucky, depending on how you see it. But you can rotate it however you want. And I tried different seamounts too. The result stands, right? So looking at the colors, the magenta here, the pink one, is the buoyancy dissipation, and the green one is kinetic energy dissipation rate, right? Averaged over the domain for these dissipations. The bottom scale here is showing the ratio of the smoothing scale. So think like model resolution divided by the width of the seamount, right? So just like so what's the smallest tail on the seamount you have compared to the size of the seamount? And I'm going to explain the scale above in a second. But as you can see, you have, obviously, as you smooth the seamount, the more you smooth it, the smaller this result, the dissipation and mixing becomes, which is the result that we've been seeing. But there isn't like a sharp drop. The drop is kind of not linear, right? Because it's a long linear law, but it's kind of constant until you get to about 0.4, right? So the L over W equals 0.4. And then, and then it becomes kind of constant, right? And you can see the difference here for dissipation is larger. Like I said, like it's about an order of magnitude. For mixing, it's about 3 times. Again, not as much, but still a lot. And if you look at the top scale here, what I'm doing is, okay, what if the seamount that I'm making it non-dimensional in a way because I'm shrinking it to scale of large-eddy simulation, what if the seamount was like the average size of the seamount in the Southern Ocean, which is about like 10 meter width, right? Sorry, 10 kilometer width, right? If you look at the data, that's about like a median size of the cataloged seamounts in the Southern Ocean. Well, then if you reach the point where your smallest feature is about 4 kilometers, you're already smooth beyond solving, right? You smooth too much and you're not getting any of the roughness. But in fact, if you smooth it if you have a resolution of around only like 500 meters, you actually already, this doesn't look much, right? Because it's a log scale, but it's already like a 2-time drop in the dissipation, right? That you have only, and 500 meters, really well resolved if you run a large scale model, right? Which is not super good news because it means that if we were to resolve this, we'd need to resolve at least for the Southern Ocean, which is where this matters a lot, with a very high resolution, and it's going to be very costly, right? So if you consider that actually with the numerics, the smallest feature you get is not the resolution of the scale, right? It's about 5 to 8 times the. It means you got to have like 100-meter grid resolution close to the South Pole to the Southern Ocean to resolve these, which is a lot of the time unfeasible, which is not good news. But okay. So how much are you? So we're not gonna. So let's assume that we don't resolve these features, which is currently the case. We're not resolving these features in most of our simulations. How much are we losing? Well, if we get the data for each seamount and we apply these curves that you can kind of match with least square methods, and you calculate the dissipation for each seamount individually in the data sets, assuming it's smooth and assuming it's rough, and then you scale it up, all the seamounts, taking into consideration the speed of the flow, the width of the seamount, etc., you get something like this. So you get two different panels of dissipation. The top here is if you assume all your seamounts are smooth, and you get this pattern. The south still dissipates more because, faster flows, more dissipation, but it dissipates way more than the rest if you assume roughness, right? If you actually resolve the roughness. And if you average it out or integrate it zonally, right? You have a curve that's like the dissipation per degree latitude on the right. And you can see that you don't lose much until you get to like minus 40 degrees of latitude. But in the Southern Ocean, there's a really big difference here, actually, if you resolve this movement, if you resolve the roughness, and if you don't resolve the roughness. And actually, if you integrate all this over the globe, it turns out to be 30% of the global seamount dissipation that you're going to miss out if you don't resolve the roughness. I mean, if you believe, I should say, because nothing is final in science, right? Until a better study comes. And in the Southern Ocean, you're missing out actually in 40% of the ocean dissipation. Picture is a little bit different for mixing, but I'm going to keep with the dissipation here, which is to say we should probably be looking into this. The difficulty is that if you look at these simulations, the horizontal shear production is a big part of the story. So these pictures, they kind of look like there's nothing plotted here, but on the left you have like smooth seamounts, and on the right, on the left you have the rough seamounts. On the right you have the smooth seamounts, and you have the horizontal shear production here on the top panels, and the vertical shear production on the bottom panel. The vertical shear production is the easiest one to capture with parameterization, right? Most of our parameterization in some way is relying on the vertical shear production. The horizontal shear production is a little bit different. I'm not aware of any parameterizations that we use in models that use the horizontal shear production. So as of now, I would argue that the only way to capture that is truly to resolve it. So this is a little bit of a call to action for us to look into ways to resolve, to parameterize these effects, taking into consideration the horizontal shear production. So in a way, this is kind of bad news because it makes it harder, right? If it was only the vertical shear production that was important, it would be much easier, but kind of bad news. And I'll end it on this bad news, I guess. Well, on this call to action, right? So the good news is that there's research to be done. And I'll leave here with the main takeaway. So first, turbulence matters. So this is what I always preach. I guess I'm a turbulence guy. I like turbulence, right? So I guess that's a little bit of my bias. So take it with a grain of salt, but turbulence matters. The Slope-Berger number actually is a very useful number to be looking at, to look at into these things. It organizes dynamics at times and the energetics really well, surprisingly well, if you take into consideration the types of different dynamics that you have. It seems that large-scale models underestimate mixing and dissipation in general, right? It seems to be more prevalent in the Southern Ocean because of the roughness thing, but in general, it seems to be the case that if you're running a Reynolds average, Navier-Stokes equation, or ROMS, Crockway, et cetera, you're going to underestimate mixing and dissipation by some extent. And the natural parameterization to bridge some of this gap, at least, is to look into roughness parameterizations, specifically roughness parameterizations that take into consideration the grid spacing, right? And I'll leave it at that. I'll leave you with the main takeaways in case you want to read them. Thank you very much. Happy to take questions. Hopefully I didn't speak too fast.
Fast enough, so it was perfect timing. Okay, so we open up the session, the question session, and you can ask in English and Spanish as you wish. We're going to start here in the auditorium, and then we move to online in case there is one. So, student question first. Okay, so we have Luis and then Manuel. Yeah.
Okay. Vamos a retar tus respuestas en español. If you wish, or unless you prefer English.
No, español también, hay que practicar.
Oye, un par de cosas. ¿Has hecho pruebas porque no vi muy bien dónde entra la amplitud de la topografía en la disipación comparada con roughness y no roughness? porque pues si la montaña tiene 100 metros de alto, disipa distinto a que si tiene 1000 metros de altura. ¿Es entra en el slope Borger number o dónde entra? ¿O no entra en ningún lado?
Entra en, o sea, el tamaño de la topografía, ¿no?
Así es.
Entra aquí, en este escala. O sea, hay también...
¿En la W? ¿Esa no es una escala horizontal o es vertical?
Es una escala, bueno, puedes hacer los dos, lo más que vas a tener un coeficiente ahí arriba, pero yo hice una escala horizontal. No, porque... Sí, de hecho puedes hacer los dos, los coeficientes, porque aquí es como una scales S, no es una escala, ¿no? Entonces, aquí para hacer eso en una igualdad, hay un coeficiente que va a entrar acá, ¿no? El coeficiente va a cambiar y a veces la organización de los datos cambia un poco. Lo intenté los dos con la altura y con el ancho, ¿no? Y cualitativamente es igual, pero cambia un poquito la organización de los datos, pero aquí es donde entra el tamaño en general, ¿no? No sé si eso preguntaste, ¿comprendí bien?
Sí, es que un poco va hacia que lo que importa es no tanto el ancho o el alto, sino la pendiente.
Ah, sí, bueno. La pendiente, de hecho, no importa, resulta que no importa tanto. De hecho, cuando yo empecé a escribir este paper, iba a explorar un espacio de parámetro tridimensional, iba a explorar también la pendiente, ¿no? O sea, qué tan steep o flat sería, pero, no, o sea, no importa mucho al final, porque intenté como, o sea, que tenía una pendiente muy grande, como que para los océanos como 0.3 o algo así, y muy chica o más normal, que sea como 0.02, 0.05, y no tuvo diferencia, ¿no? La única parte del espacio de parámetro que hubo un poquito de diferencia con la pendiente es si estábamos en un shallow water, porque eso todo fue como deep water, ¿no? Entonces, como no ves ahí la superficie. Si está como shallow water, hay un poquito de dependencia en la pendiente, pero no tanto. Es mucho menor que la dependencia en el número de Rossby de Fruit.
Oye, y nada más en las simulaciones, las del headland, ¿eso se supone que se resuelve hasta qué? ¿Hasta 1 metro?
Las simulaciones que yo hice, sí, sí.
O sea,
la vertical es 1 metro. Porque por la large-eddy simulation hay que resolver hasta que los eddies estén como isotrópicos. Y en el océano generalmente eso es la escala de Osmedov, que generalmente está como 1 metro, 2 metros. Entonces, todos los large-eddy simulations que vas a ver generalmente son 1 metro de spacing.
¿Y cerca de la frontera hay un tratamiento especial o en
la frontera abajo o arriba?
Las sólidas, las de abajo.
Sí, al metro, no hay un tratamiento especial, nomás lo que hago es que por la representación de la bathymetría que hay, no son artefactos, ¿cómo se dice? Artificios.
Trucos.
Artificios numéricos. No, yo no estoy considerando los 5 o 6 primeras celdas cerca de la bathymetría para no contaminar pues, los resultados. Pero sí, intenté con ellos, también con estas celdas, y también el resultado no cambió. Se cambió un poquito cuantitativamente, pero calitativamente es lo mismo, ¿no? Con o sin esas celdas muy cerca de la bathymetría. Pero los que presenté aquí no los estoy considerando.
Gracias.
Te contesté bien, ¿no?
Pues gracias por tu plática, estuvo muy buena. Yo te quiero hacer una pregunta muy básica, ¿no? Bueno, básica para ti. ¿Cómo cuantificar? ¿Qué es lo que nos estás enseñando cuando es mixing?
Bueno, buenísima pregunta. El mixing de verdad yo tendría que hacer, si hubiera el mixing rigurosamente, es la destrucción de la energía potencial disponible. Pero es muy difícil hacer eso, entonces lo que hago es hacer la destrucción de la variancia de flotabilidad y multiplicar o dividir por un coeficiente, no me acuerdo, y hice unas pruebas y bueno, por la teoría se supone que son muy parecidos, ¿no? Y mis pruebas sí eran casi iguales. Entonces lo que estoy haciendo de verdad es calcular la destrucción de la variancia, de la flotabilidad y dividir creo que por por n al cuadrado o algo así, y eso es lo que estoy llamando de mix, de mezcla. Sí.
Puedo hacer otra pregunta. Mira, a raíz de lo que le dijiste a Luis, de pendiente no importaba mucho, surgió la pregunta. Bueno, supongo que aquí parte de la mezcla la hacen las ondas internas, ¿no?
Sí.
Pero pues a las ondas internas como que sí les debería de importar
sí.
la pendiente, ¿no? Porque van a, si es crítica, subcrítica, tipo de cosas, ¿no?
Sí, y es muy buena pregunta. Y yo sí calculé eso, a ver si tengo el slide. No lo puse acá. Pero sí, la disipación por las olas, ¿no? ¿Cómo? Ondas, ¿no?
Ondas
por las ondas. Sí cambia un poco con la pendiente, pero en mis simulaciones no mucho. Pero el problema es que yo no confío mucho en la generación de ondas internas en mis simulaciones, porque la topografía no está muy bien, o sea, la topografía que yo tengo acá es como una topografía si ubicas que de full step, o sea, es como un Lego, ¿no? O sea, es como toda, sí, no es algo continuo. Entonces, yo no confío mucho en las generaciones de las ondas en esta simulación, por eso no estoy investigando eso. Vi una diferencia, fue poca, pero no confío, entonces hay que investigar más. Pero es un muy buen punto.
¿Alguna otra pregunta aquí en el auditorio? Sí, Julio.
Bueno, serían dos porque, digo, continuando con esta, pero entonces, ¿qué? O sea, ok, no te interesa, pero entonces, ¿qué causa el mixing? Porque...
¿Qué causa mixing?
Bueno, o sea, la turbulencia, pero uno piensa en internal wave breaking o cosas así, ¿o no? ¿O hay algo más que eso?
No, internal wave breaking también causa mixing, ¿no? Aunque no estoy viendo eso acá, pero más lejos, o sea, generalmente más después. Acá, lo que más causa mixing son las instabilidades de shear.
Ok.
¿No? Hasta las shear como chiquitas o de shear que vienen de las instabilidades simétricas.
De las simétricas, ¿no? Ok, ya, perdón. Bueno, y no sé si podías explicar, cuando haces simulaciones LES, pues lo que pasa es, en vez de con Reynolds se aplican filtros, ¿no? ¿O no? O sea,
sí.
No sé si podrías para los alumnos un poco explicar.
O sea, la teoría de
bueno,
LES,
¿qué
¿no?
es lo que se hace que sea diferente un poco al RANS?
No, sí, perfecto. Bueno, a ver si puedo hacerlo en español. Si no, cambio al inglés. Pero lo que hacemos en el large-eddy simulation, en LES, es que empezamos con la ecuación de Navier-Stokes, ¿no? Normal. Y hacemos un filtro matemáticamente en las ecuaciones, ¿no? Y si haces eso, es una manera muy formal de hacer las cosas, ¿no? Entonces pasas un filtro y resuelve una ecuación que es igualita a las ecuaciones de Navier-Stokes, pero para las velocidades filtradas, no más que hay un término agregado allá, que es un estrés de Reynolds, o algo parecido con eso, ¿no? Un término de estrés, subfilter scale stress, así se dice en inglés, un estrés de subfiltro, no sé. Y ese término es lo que es que no logramos simular, no logramos correr, no sabemos, no tenemos información suficiente para saber precisamente qué es este término, entonces hay que hacer una parametrización, un closure de ese término. Y como el filtro, hacemos la suposición de que el filtro está en una parte de la escala donde los vórtices, los remolinos ya son isotrópicos. Podemos utilizar unos insights de la teoría de Kolmogorov y se supone que va a ser un closure, una parametrización que va a ser universal, que los remolinos isotrópicos son, por buena aproximación, universales. Entonces es un tipo de parametrización que si llegas a una resolución donde tus vórtices, tus remolinos son isotrópicos, se supone que lo hace muy bien. Entonces esa es la diferencia entre hacer un Reynolds average Navier-Stokes equation como un ROMS, un CROCO, un MIT-GCM y un large-eddy simulation. Es donde está tu filtro, ¿no? Y el filtro generalmente es la malla, ¿no? Lo suponemos que el filtro es la malla. ¿Dónde está su filtro? Y el facto que el filtro es formal y matemático en la large-eddy simulation. Generalmente en Reynolds average, en el croco es una cosa más ad hoc, no sé cómo se dice. Sí. No sé si me hice entender, me hice comprender.
Sí, gracias, muchas gracias, Tomás.
¿Alguna otra pregunta aquí en el auditorio? Sí, tenemos a Alejandro y Sheila. Dale, Sheila, adelante.
Bueno, muchas gracias. Yo la verdad que estoy contenta porque nunca se habla de mixing y yo también amo la turbulencia, así que gracias. Y también el otro gracias es por hablar de la escala de Ósmido, porque varias veces mis estudiantes dicen que esa escala nunca la usamos para nada y por fin les has dado una aplicación. A ver, no sé si andan por aquí, pero bueno. No, mira, una pregunta, tiene que ver justo con este mapa, que a veces llama la atención las zonas que están más en blanco, y en especial me voy al Golfo de México. Y entonces dices, ¿qué pasa en esas zonas? Es que los seamounts no son importantes, son pequeños, son grandes, son...
De hecho, no sé.
No sabes,
sé,
¿no?
La verdad es que no sé. Eso es un dataset que toda la gente usa. Es un dataset de 2010, creo, de unas personas que no son de oceanografía física, son Kim y Wessel, son sus apellidos. Y lo hicieron por satélite, de hecho, porque ya ves que los Seamounts, ¿no? Tenían una signature en la superficie, ¿no? Una señal en la superficie y puedes como inferir, no sé.
Sí, la inferían, sí.
Y por alguna razón no salió nada aquí en el Golfo de México. No sé si porque no hay muchos o simplemente porque la técnica no está buena para la física del Golfo. De verdad no sé. Pero
Digo el Golfo, pero hay otras zonas. Entonces,
sí, acá,
no ejemplo, se considera igualmente como un sesgo en el resultado general. O sea, sí seguimos pensando que en el sur hay más y ahí
sí, por ejemplo, aquí en el sur, seguro que hay más acá que para acá por el hielo, ¿no? Que hay mucho por acá.
Claro.
Y aquí, por acá también hay poco. No sé si hay o no acá, pero lo que sé es seguramente eso no son todos los seamounts que existen, ¿no? Ellos estiman, creo que esos son 20,000 seamounts, es el catálogo, algo así. Y ellos estiman en su paper que existen como 30,000 seamounts. Entonces, no todos, porque algunos son más chicos o que están muy juntos unos de los otros, es más difícil. Y hay gente que habla de 50,000 y ahí empiezas a discutir, pues, ¿qué es su seamount? ¿Qué tan chico es?
Claro,
entonces ya no sé, pero no son todos. Hay más que lo que está acá.
Sí,
yo no sé precisamente por qué aparecen en algunos lugares y no otros. Pero es buena pregunta, no me había percibido.
No, porque en el Golfo luego tenemos, cuando vas a modelarlo, tenemos muchos problemas que tienen que ver con la rugosidad justamente de la bathymetría y de hecho a veces te crea más mezcla espuria, ¿no? que realmente suavizarla. No sé, está interesante el trabajo. Y lo otro es, digo, otra cosa que siempre se batalla es justamente con este épsilon, cuando vas y lo mides, y con microestructura, luego no tiene nada que ver con las parametrizaciones, ¿no? ¿Cómo ves esa conciliación a largo plazo? ¿Algún día vamos a llegar a poder parametrizar si tenemos en cuenta todas estas cosas o no? ¿O nos olvidamos y seguimos?
Es difícil.
Con teoría.
Yo creo que yo no soy la mejor persona para contestar eso porque nunca he participado de un esfuerzo de parametrizar, poner una parametrización en un modelo. Lo que sí creo es que con los avances de hardware y software vamos a poder... Bueno, es que ahora estamos en una ¿cómo dijiste? Como ventana gris, ¿no? La gray zone. Estamos haciendo modelos que estén más y más bien resueltos, ¿no? Y estamos en un lugar del espectro donde no sabemos si está mejor parametrizar o no parametrizar, resolver, porque resolves algo, pero no todo, parametrizas todo, pero no hay que parametrizar todo, porque estamos resolviendo un poquito, no sabemos qué hacer. Entonces, lo que sé es que creo que en algún momento vamos a tener, para tener un buen resultado, vamos a tener que sí hacer un esfuerzo para las resoluciones estar más grandes. Pero hasta que lleguemos allá, porque eso puede ser como 20, 30, 40, no sé, hay que hacer esfuerzos para hacer parametrizaciones que lleven en consideración el spacing, ¿no? La resolución de la malla. Pero no sé bien cómo hacer eso. Creo que nadie sabe bien cómo hacer eso, porque no existe todavía en el océano, ¿no? Pero sí, no sé, yo no soy una buena persona para responder eso, pero...
no creo que haya ninguna buena persona, pero era importante tu opinión. Gracias.
Sí, gracias por la pregunta.
Ale, acabas.
Tomás, muchas gracias. Muy interesante tu presentación, tu trabajo en general. Tocas desde varios temas que me interesan mucho, que es flujo topografía y es la dominancia de los flujos que van en el sentido de las ondas, de viaje de las ondas atrapadas, ¿no? Una pregunta, tú diste la mala noticias y por antes regresamos a lo que preguntó Sheila, de que las cosas necesitan mejorarse. ¿Crees que haya alguna forma de, con los datos que tú tienes, tratar de parametrizar al menos localmente o por periodos específicos la disipación o la mezcla con base en los parámetros que tú tienes, nada más? Suponiendo que yo tengo una región en mi modelo, tengo ahí una montaña, un headland, que yo pueda hacer localmente alguna estimación de la disipación.
Bueno, yo creo que bueno, si quieres hacer algo que sea solo para siempre estar bien en una zona muy específica, creo que sí es posible, porque hay maneras de cambiar los coeficientes, pero si ya cambias la zona y vas a hacer otra cosa en otro lado, con otra geometría, probablemente ya no va a ser suficiente. Y yo creo que hacer algo general está difícil por eso. Por el facto de que la producción por shear horizontal es importante. Y entonces eso creo que nadie sabe muy bien cómo poner eso en una parametrización. Al menos yo no conozco, yo no he hablado con nadie que sepa, y yo seguramente no sé. Probablemente hay una manera, pero yo no sabría decirte de verdad. Intentamos, por ejemplo, hacer algo con KPP. ¿Dónde está? Acá. Y en algunas maneras, hasta, ¿ves? Por ejemplo, cambiamos un poquito los coeficientes de KPP y a ver si logramos que sigan las curvas que tengo, ¿no? Y en algunas partes sí sigue más o menos bien, solo necesitarías una modificación aquí para el Resumen number negativo, ¿no? Cuando está en convección, pero en algunas otras partes es muy malo, entonces sí está difícil. Entonces, no sé.
Muchas gracias por
Abrimos oportunidad para los que están en línea. Si alguien en Zoom tiene alguna pregunta, puede abrir su micrófono ahora. En Zoom no tenemos a nadie y tampoco tenemos todavía preguntas del resto de las redes. Si me permites nada más una última, Tomás, más de la parte que tiene que ver con la parte práctica o técnica de tu trabajo. Sospecho que aquí quizá hay algunos estudiantes que están interesados a lo mejor en hacer simulaciones similares, y entonces si nos platicas un poquito nada más pues, hiciste todo esto con Oceanic y, o sea, ¿qué tanto poder de cómputo se necesita? ¿Se puede hacer en una laptop? No. ¿Qué tanto tiempo dura?
Bueno, podrías hacer una versión muy coarse,
muy light,
muy light, con resolución muy mala en tu laptop, pero de ahí ya no podrías estar en la escala de Osmond, lo que es importante. Entonces, yo no confío en esos resultados de large-eddy simulation de LES. Lo que yo hice, todas estas simulaciones están hechas en una GPU solo, y creo que las primeras de la Headland fue una GPU, una V100, like V100 de NVIDIA, y las otras fueron una GPU A100, ¿no? A100 también de NVIDIA. Y el importante, generalmente el factor limitante cuando vas a correr esas simulaciones no es la velocidad, porque corren de verdad muy rápido, porque Oceanic en GPU es muy rápido. Por ejemplo, creo que fue la mayoría de las simulaciones acá, a ver si tengo, por ejemplo, de estas, en un día estaban listas ya, ¿no? Y si no el factor limitante es la memoria, ¿no? Entonces, esta A100, la A100, tenía 80 gigabytes de memoria, pero ahora ya hay GPUs que hay mucho más, y si quieren hacer algo así, de esas simulaciones sería posible en una GPU de estas, una A100. Si quieren hacer simulaciones más grandes, o GPUs más nuevas o más recientes que tienen más memoria, o tienen que hacer más de una GPU en paralelo. Pero si tienes la GPU, ¿no? Es muy fácil hacer esas simulaciones, porque el código, todo todo mi código en todos los papers, todos los artículos que he publicado en mi vida están en GitHub. Entonces, si tienes el hardware y si puedes instalar Julia ahí, puedes hacer todas las simulaciones igualitas, ¿no? Con un comando. Nomás tienes que tener una GPU, ¿no? Bueno, pero si tienes, está fácil.
Sí, aquí hay. Aquí va a ser
Bueno,
Sheila
fácil.
el anuncio. Hay
Fácil,
dos.
fácil.
Hay dos, así que se va a poder. Ok, bueno, pues nada, échenle un ojo a su GitHub. Ahí también, bueno, lo encuentran fácil, Tomás Chor. Y bueno, pues nada, muchísimas gracias,
Gracias.
Tomás.
Gracias.